Hello and welcome back. In 13.2, we get to work with Euler paths and Euler circuits. So this section, by the way, is assuming that you've already understood all the previous vocabulary, what a graph is, vertex, edge, loop, degree, parity, things like that. So we'll start with another definition. So a path that uses each edge of a graph exactly once is an Euler path. So it still has to meet the definition we saw in the previous section about what it takes to be called a path. Euler circuit is a little bit easier of a definition. Euler circuit is just an Euler path that starts and ends on the same vertex. All right, so let's take a look at some examples. We'll connect Alpha and Charlie, Charlie and Echo, Echo and Bravo, Bravo and Delta, Delta and Alpha. So a nice pretty little star. So here we can go from A to C, from C to E, from E to B, from B to D, and from D back to A. We have 1, 2, 3, 4, 5 edges used. 1, 2, 3, 4, 5 edges used, and there are only 5 edges. So all 5 edges used means this is an Euler path. The fact that it begins and ends on the same vertex tells us this is also an Euler circuit. Okay, as for our next guy, we'll do Alpha, Bravo connected, Bravo, Charlie connected, Charlie, Delta connected, Delta, Echo and Charlie connected. So for this one, I could go from A to B, from B to C, from C to E, from E to D. So let me just sort of cross them off as I go. So A to B, B to C, C to E, E to D. So the only edge I haven't used yet is taking me back to C. So I've used every single edge on there. That is one thing you can do, is lightly cross them off in a different color to sort of keep track of, okay, did I use that edge or did I not use that edge yet? So this one, all edges are used that appear on the graph. So this is an Euler path. There's no way that I could return to A, however, so this is not an Euler circuit. All right, let's take a look at graph 3 here. Alpha, Bravo, Charlie, and Delta. And this one, you can pause and take a minute if you'd like and see if you can find an Euler path on this. You should discover, however, that no matter how hard you try, no matter which of the 4 vertices you start on, you're not going to be able to use each edge once. So go ahead and pause it, give it a try, convince yourself that what I just told you is correct. Welcome back. So this is a case where we have no Euler path. And if there are no paths, there can't be any circuits. And here, let me go back and name these guys. So we're going to name this guy G1. So our previous one with the 5 edges. We'll name this guy G2. This guy G3. G4. Let's see. We have Alpha, Bravo, Charlie, and Delta again. A and D is connected. D has a loop. D and C are connected. C and B are connected. And B and D are connected. So on this one, I'm going to ask you to pause it, see if you can find an Euler path. And answer the question, is it also an Euler circuit? Okay, so go ahead and pause, see if you can answer those two. Welcome back. So for this one, graph 4, you should have been able to find an Euler path. For example, you could have gone A to D, D to D again. So because of that loop, we are listing the vertex D twice in a row. So that's this edge and this edge taken care of. From D, maybe you want to B next, which means then you went to C, and from C you went back to D. So that is an example of an Euler path. This was not an Euler circuit. Let's see, what else could we have had? D to D again. I'll do this one in blue. So starting at the loop, and then to C, to B, back to D, and up to A. That also used every single edge available on the graph. It was also an Euler path, not an Euler circuit. And you might have noticed that even if I didn't use yours, that yours either started with an A or ended with an A, started with a D or ended with a D. That's not coincidence. To know why this is, we look at degrees. So let's go back to graph number 1 and look at degrees. So vertex A is degree 2, vertex B is degree 2, vertex C, degree 2, vertex and degree, vertex D, degree 2, vertex E was degree 2. And on this one, okay, everybody was degree 2, and we were able to find an Euler path and circuit. So see if you can complete that information for graphs 2, 3, and 4. Vertex and degree. Go ahead and pause it, unpause it when you're done. Okay, welcome back. So graph number 2, vertex A had a degree of 1, vertex B had a degree of 2, vertex C was degree 3, vertex D degree 2, that's an ugly 2, there we go, and vertex E also a degree 2. And on that one we found a path but not a circuit, and notice that our path began on an odd degree, ended on an odd degree, but we were unable to find a circuit. Hopefully you did graph 3 already. Vertex and degree. So our vertex A had degree 1, vertex B degree 3, vertex C was degree 1, vertex D degree 1 as well. This one, all of our vertices had odd degrees. Graph 4. A had degree 1, and notice that our Euler path either began or ended on that odd degree. B had degree 2, C had degree 2, and D had degree 5. So 1, 2, 3, and don't forget to count the loop twice for 4 and 5. So all of our Euler paths for that one either began or ended on an odd degree. And it turns out that in general, the number of odd vertices tells the story on whether there's an Euler path or an Euler circuit. We do have to meet this criteria to use Euler's theorem. We have to have a connected graph. No odd vertices. Then there exists at least one Euler path and circuit. There could be more, but there's at least one. 2. Exactly 2 odd vertices means there is at least one Euler path. So it should be capital. No Euler circuit. So exactly 2 odd vertices. No, I had that odd looking, strange looking odd. 2 odd vertices, at least 1 Euler path, no Euler circuit possible. Basically, because we have to begin on one odd and end on the other. More than 2 odd vertices. No Euler path, no Euler circuit. All right, so let me example with more edges than we've been playing with recently. Let's see. Yeah, that should be sufficient. Okay, so take a minute and copy down what you need from there. And recall, places where the edges meet don't guarantee there's another vertex there. Unless I specify there's a vertex there, there is not a vertex there. So on this one, without looking to find it necessarily, is there an Euler path? Well, this is a connected graph, so it's at least possible I can get from any one vertex to any other vertex. Might take a couple stops, but I can get there. Well, to do that, I just need to find the degree for each vertex. So vertex A, degree 3. 1, 2, 3 pass off of A. Or edges, I should say, off of A. Vertex B, degree 2. Vertex C, also degree 2. Vertex D, degree 2. Vertex E, degree 2. Foxtrot, degree 2. Golf, degree 2. And hotel, degree 3. So yes, there is an Euler path. But no Euler circuit. And any Euler path will have to either begin or end on A and do whichever other on H. So for example, we'll just do one example of an Euler path. Again, there are others. I can go from H to A, from A to D, from D to G, from G to B. From B, I have to go to E. From E, back to H. From H, my only option now is C, because the other guys have been already used. From C, I have to go to F. And from F, there's our last edge connecting with A, which was our other odd vertex. So that is one example of an Euler path. Not the only one, certainly. We could do the same path backwards. There's different ways we could have taken it. Well, notice this idea of can we use every edge exactly one time? That's exactly the question that started us in this chapter, the famous Keinsberg bridge problem. Let's see, it's got umlaut over the hole there. I think that's what it's called. But pronunciation, it sounds like Keinsberg. So if you'll recall from the beginning last chapter, landmass above and below, two islands, two bridges on each side of the big island, one on each side of the little island, and one bridge connecting them. So let's go ahead and represent this in graph theory form. So the northern edge we'll call A, big island we'll call B, little island we'll call C, southern land D. So let's see, A to B, two edges connecting A and B. A to C, one edge connecting those guys. B to C, one edge connecting those guys. B to D, two edges again. And D to C, one edge. So, is there a way that we can take every bridge exactly once without resorting to some type of trickery that violates the spirit of the question of can you just walk on dry land, not swim, not fly, not catapult, not ice skate? I've heard of a million different versions of it. Can you keep with the spirit of the question and use only bridges and walking on land to do this? No, we just need to list each vertex and the degree. Vertex A, degree 3. Vertex B, 1, 2, 3, 4, and 5 there. Vertex C, degree 1, 2, 3, and already we see we're in trouble. We have more than 2 odd degrees. Vertex D happens to be another one, but as soon as we get more than 2, D happens to be degree 3. So there exists more than 2 odd vertices. That means there is no Euler path. Also, no Euler circuit. To be a circuit, you have to be a path to begin with, and we've shown that this can't be a path. So the Keinsberg bridge problem, this was a way that Euler was able to show that no, it's actually not possible to walk each bridge exactly one time without needing to walk a bridge a second time. So then the next thing I want to go over is the idea of an algorithm that would create this for us. So with these smaller graphs, it wasn't too bad to just sort of use trial and error to create this. But the question arises, what if we had, say, 60 vertices and, I don't know, 200 edges? Well, at that point, trial and error may be a little tough. We'll just say not practical. So out comes our friend Flurry. So an algorithm is like a set of instructions. A recipe, if you will. So the first step in Flurry's algorithm says, okay, well, see if we're even looking for something that's there. See if an Euler path exists. If yes, then proceed. If not, done deal. We're not going to be able to find it if it doesn't exist at all. If there are 0 odd vertices, start anywhere. Two odd vertices, start on odd. Trace path, numbering each edge. So basically numbering them as you're using them so that you can go back if you get stuck or make a mistake. If 2 edges are possible, in other words, if you're at vertex A and you're choosing between going to B and C, use one that is not a bridge. And you just continue in that manner until you've numbered every single edge. All right, right, so some examples. Let me put the labels on these so that you can kind of follow along with where I'm putting these. Bravo, Charlie, Delta, Echo, Foxtrot, Golf, Hotel, India. Okay, so we're going to use Fleury's algorithm to find an Euler path. Possibly an Euler circuit. So first we need to list out our vertices and degrees. So vertex A, degree 3, vertex B, degree 2, vertex C, degree 2, D, degree 1, 2, 3, 4, E, degree 2, F, degree 1, 2, 3, 4, G, that's an ugly G, but that's a G right there. G is degree 2, H, 1, 2, 3, 4, 5, and I is degree 2. So we look for the odd vertices. So A and H are the only odd vertices. So 2 odd vertices. We have an Euler path. No Euler circuit. It says to start on one of the 2. Arbitrarily, I'll start on A. So I'll go A to B. There's only one place I can go from there, so B to C, C to D. And then here's the first place where we have a decision to make. This was part of Fleury's algorithm. He said, if you have a choice of where to go, and we do, we have 3 more paths that we can use to leave D, it said don't use a bridge. So maybe I'll dip down here to E for number 4. Move number 5 has to take me over to A then. Move number 6 takes me back to that D. Now I no longer have a choice. I've burned up all of the other edges. Now I have to use the bridge. So 7 takes us across to F. I have a choice. None of these are bridges, so it doesn't really matter which way I go. So maybe I'll go across to H, down to I, up to F again. And now there's only one more path off of F, so we'll do that for 11. G takes me back down to 12. That gets me back to H. And lucky number 13 is our loop. So our Euler path, we'll just kind of trace it out. We have A to B to C to D to E, back to A, across to D, to F, to H, to I, to F again, to G, to H, and to H again on the loop. So we do list that last one out twice. So that is, again, an Euler path, not a circuit. It's not a circuit. It didn't begin and end on the same letter. Again, this is not saying that this was the only Euler path that exists. It's just saying that this was an Euler path. So one more sort of practical example that we can use on these. If we have these, a map of, say, a subdivision, and the vertices are intersections of streets, and the edges are streets. So this neighborhood obviously not designed on the nice pretty grid program that Chicago used for most of its neighborhoods. Okay, so I'll just arbitrarily label our intersections. So intersections are vertices. Looks like we used A through L. So in this one, this would be an example of, is it possible to patrol the neighborhood? One L. I don't know what I was doing there. Drive each street exactly once. And if so, can the car start and stop at the same point? So if yes, that's where you want to build your station. If not, then you just have to sort of plan accordingly. So our vertices, vertex A, degree 2, vertex B, also degree 2, vertex C, degree 2, vertex D, degree 2, vertex E, 1, 2, 3, 4, 5, 6, messy intersection, vertex F, 1, 2, 3, 4, 5, 6 again, vertex G, degree 2, vertex H, degree 2, vertex I, degree 1, 2, 3, 4, 5. 1, 2, 3, 4. My apologies. 1, 2, 3, 4. Vertex J, 1, 2, 3, and 4. Vertex K, degree 3. And vertex L, degree 3. Okay, so is it possible to patrol the neighborhood and drive each street exactly once? For that one, that is a resounding yes, because there is an Euler path. Can the car start and stop at the same point? Unfortunately, on that one, there is a no on that. But if you put a station between K and L, you can do a reasonable job of patrolling, hitting each street exactly one time while you're out. You may hit that last one between K and L since they happen to be adjacent. You'll hit that one on the way out and on the way back in. But all of the other streets, it would be possible for you to do just one time. So there does exist some Euler path. You can find one on your own. So some problems I would recommend. So this is section 13.2. I would try 1 to 6 all, 7 to 49 on the odds. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.